recording. And so we're very glad to have Maru Sarazola bright and early in the morning from Cornell talking about the stable homotopy hypothesis. So you can start whenever you're ready. Maru, thank you.
Yes, thanks, John, for the invitation to speak here. So like the title says, I'm going to be talking about some work that we did with my co-authors, Lynn Moser, Victoria Zornova, Simona Pauli, and Paula Verdugo on the stable homotopy hypotheses. So the way that this talk is going to go, we're going to start off by talking a bit about the classical homotopy hypotheses. This is something that you might have heard before, so we're going to do like a literature review of sorts. And once we do that, I'm going to explain one specific model that one can use for the homotopy hypotheses, and then we're going to move to the stable version and look at some new results. Right, so the first part, like we said, is on the classical homotopy hypotheses. Nothing that I'm going to say here is new or due by us at all, but it's just meant as a refresher for the stable version to sound a bit more familiar. So what is the homotopy hypothesis? Well, this is the statement that topological spaces are the same as infinity groupoids. And now, for the purposes of this talk, I am only going to care about homotopy theory. So when I say the same, what I really mean is they have equivalent homotopy categories. So that's the most general version of the statement. There's a more refined version where we identify level n, and we get the statement that n types are the same as n groupoids. So you can see that this is a statement that compares something of a topological nature to something of a categorical nature. And let's go a little bit more in detail on what are the things involved in the homotopy hypotheses. So on the topological side, we have these n types. These are just topological spaces whose homotopy groups vanish outside of n. And we have this homotopy category where we invert the weak homotopy equivalences. So the maps between spaces given us isomorphisms on all the homotopy groups. So the topological side is quite easy to define, and it's something that should be more or less familiar to all of us. So what goes into the categorical side? Well, n groupoids, and here's where things start to get a bit more complicated, because n groupoids are different things depending on whom you ask. So while we all agree on what the topological side is exactly, there's no such consensus when we talk about n groupoids. So there are many different models of n groupoids out there, but of course we're not going to go ahead and call anything an n groupoid. They do have to have some theme in common. So what we generally agree upon is that anything that we call an n groupoid should consist of some variant of higher, meaning n category, with all cells invertible above level 0. So what is this going to look like? We are going to have 0 cells that we think of as objects, and then between 2 0 cells, I can have a 1 cell that we think of as an arrow. And now if I have 2 1 cells like this, I'm allowed to have a 2 cell between the 1 cells. And if I have another 2 cell between the 1 cells, I'm allowed to have a 3 cell between them, and so on and so forth. And so this is the higher n category part with cells all the way up to level n. And for the groupoid part, we ask that all of these arrows that I've drawn here have inverses. So in fact, finding a very precise definition of n-groupoids that one can actually get their hands on and that satisfies the homotopy hypothesis is a non-trivial thing to do. And it's even informed the foundations of category theory. So you can think of the homotopy hypothesis as a sanity check whenever you want to use a different model of n-groupoids. So there's no reason for us to worry about this multiple models out there, because like we said, I really only care about homotopy theory here. And then since we expect all of these models of n-groupoids to satisfy the homotopy hypothesis, that means their homotopy categories have to be the one of spaces. So in particular, they all have the same homotopy category. So we can, let's say, freely move between models if we want to do so. All right, so this is very, like a very hand-wavy definition of what an n-groupoid is. I will go into a bit more details on a specific model in a bit, but so you will get to see something a bit more precise. But for now, allow me to use this idea to give you some intuition about why the homotopy hypothesis makes sense. So remember, that was the statement that topological spaces are the same as infinity groupoids. And if this is the first time that you see this statement, or if you haven't thought about it much, it might seem a bit weird. Like we're comparing things that a priori are of a very different nature. So the way in which we can intuitively see what's behind this is by looking at spaces in a slightly different perspective. So say we have our topological space. I want you to think of the points of the space as being objects, and then between 2 points, I can have a path. So think of the paths between objects as one cells. And now let's say I have a different path. I can have a homotopy that deforms one path into the other. And then if I have another homotopy, I can have a homotopy between them. And at this point, this picture should be looking very similar to the one that I was drawing for the n-groupoids. So this is the perspective from where we make the connection between these spaces and these things with higher cells. All right, so the lower cases of the homotopy hypothesis are in fact pretty familiar. So if we look at case 0, on the categorical side, we have 0 groupoids. So these have cells only up to level 0 and nothing else. So these are just sets of 0 cells, which we think as just like points, right? Just objects. On the topological side, we have 0 types. So these are spaces that may have a non-trivial pi 0. So we may have a bunch of different connected components, but then above that, all homotopy groups have to vanish. So each of these connected components are going to be contractible. So if we just pick a point representing each of these connected components, then up to homotopy, this is the same as just a set of connected components. So for n equals 0, we are just getting the statement that sets is the same as sets, pretty much. N equals 1 is less trivial, but still quite familiar, since this is the correspondence between one types and groupoids that we have by the fundamental groupoid functor. So if we have a space, then we define the fundamental groupoid of the space as a category. So this is going to be the category having as objects the points of the space, and as morphisms, I want to say paths in the space. However, if I want to get a category, I'm not going to be able to have identities in associativity if I just take paths. So I'm going to take homotopy classes of paths in X to make everything look nice and just happen on the nose. So this is a category, and like we said, we can invert paths up to homotopy, right? If you run a path in a space, then you can say parameterize it and run it backwards, and you get an inverse up to homotopy. So this is in fact a groupoid. And for the other direction, if you start with a groupoid, then in particular, it's a category. So you can take its realization and you get a space. And if you study that space, it turns out this is an Eilenberg-MacLane space. So it is in fact a one type, and one can show that this gives an equivalence on the homotopy categories. So cases 0 and 1 are perfectly fine, but then things start to get a bit more complicated. And in fact, one can prove that for n greater than 2, these strict n groupoids, where I'm trying to make associativity and unitality work on the nose, are not going to be enough to model n types. And what we're going to need is a weaker type of higher structure, where associativity and unitality of composites only works up to higher data. So how does one define such a thing? Well, we need to find some combinatorial machinery, and I apologize ahead of time if some of you actually does some combinatorics. This is probably a bit offensive, but this is what topologists call combinatorics. So we need to find some machinery that encodes all the relevant data. So that's going to be, we want to record the cells and the dimensions from 0 to n. We want to record the composites of these cells and also the data of the associativity and unitality. And then, of course, we are eventually going to want to take a homotopy category of this. So we need to have some version of equivalences also recorded into this machinery. So here's where I was saying there's plenty of ways to do this in the literature, but one such way is to use multi-simplicial sets, because we can encode compositions using the Siegel maps. So now I'm going to tell you a bit about a specific model. So this is going to be one of these multi-simplicial models I was talking about. So first, let me remind you what the Siegel maps are. Let's say that we have a simplicial object in a category C. So this is simply a functor from delta op to C. So whenever we have such a functor, we can consider the following picture. So for each k greater or equal than 2, we take k many copies of x1. So if you think of these as just simplicial complexes, x1 are what we think of as the intervals. So we take k many copies of all the intervals that we have. And then we have maps. So x0 are going to be the points, and we have maps that pick out the starting point in the interval and the ending point in the interval. And then we take this picture and we take the pullback. That's why we have this condition up here. So since we have maps to all of these from this xk collection of k simplices, the universal property of the pullback means we will have a unique map like here from xk to that pullback, and that unique map is what we call the kth Siegel map. So let me run this for a low case. Let's run this for k equals 2, just to see what this Siegel map is doing. So for k equals 2, what we have are x0, which we think of as points. We have x1, which we think of as segments. So these have a starting point and an ending point. And then we have x2, which we think of as triangles with oriented segments being their sides. All right, so what is the Siegel map in this case? Well, you can double check, but if you trust me, these V maps here are exactly going to pick out, so V1 is going to pick out this side of the triangle, V2 is going to pick out that side of the triangle. So the Siegel map, which goes from x2 to the pullback of x1 and x1 along x0 is going to start with a triangle, and it's going to pick out these composable sides. So this picks out the composites. So this is why we're going to be using this map to somehow encode the data of how we can compose in our structure. All right, so now I want to give you a glimpse of one specific model. This is the one that we chose to use for our paper, and it's called Thompson-Samani N groupoids. So this part is going to be a little bit technical. I'm not going to go into all the details because that would take a really long time. But it's not going to be crucial for the rest of the talk that you understand every detail here, but I do want to give you just an idea of what kind of creature we're dealing with when we talk about the homotopy hypotheses. So these are going to be what we take, the model that we take for higher N categories, and these are defined by induction. So I'm going to define Tom N, which is going to be the category of Thompson-Samani N categories, and I'm going to say Tom 0 are sets, and the notion of equivalences between sets that we take is bijections. Tom 1 is just cat, so a Thompson-Samani 1 category is a category, and the notion of equivalence there is that of equivalence of categories. And then for higher N, this is where the induction kicks in. We are going to say a Thompson-Samani N category is going to be a functor from n-1 copies of delta op into cat, which if we think of cat as living inside of simplicial sets through the nerve, this can be seen as a functor from n copies of delta op to set. And then we need to satisfy some conditions. So we ask that when we fix the first simplicial dimension, that x0 is discrete, that xk is of the sort Thompson-Samani n-1 for every k greater than 0. And then we ask that for all k greater or equal than 2, these Siegel maps have to be of the appropriate kind of equivalences. All right, so what are the important features of these Thompson-Samani things? Well, we have multi-simplicial objects, so that means we have a lot of simplicial dimensions for each copy of delta op, and we will have Siegel maps in all those simplicial directions, and we require those to be whatever the right notion of equivalence is. So how do these record all the data that we said we need to record? Well, let's look at the cells first. The cells are going to be encoded in some of these discrete sets. So X0 will record the set of 0 cells, and then X111 are many times 0 will record the R cells, and this is why we are asking for these to be discrete, because we want to have a set of cells, not a space of cells. And then for the highest 2 kinds of cells, we are going to take X of 1111 n-1 times. So remember, our X goes from n-1 copies of delta op into cat. So if we fix all n-1 directions, we just end up with a category. And we're going to say that the objects of that category are the n-1 cells, and the morphisms of that category are the n cells, which makes sense because we know that k cells are supposed to be like maps between k-1 cells. All right, so this is how we record the cells. How do we record their composites? Well, the main reason why we are using this model at all is so that we can use the Siegel maps to record the composites. So if we want to compose 2 things here, let's think of them like that, then we are going to use the fact that we are asking that it be an equivalence. So that means up to homotopy, we can run it backwards. So it's like up to homotopy, we can fill these composable arrows to a triangle, and then we can go ahead and take the lower segment of the triangle, and we're going to take that as the composite. So up to homotopy, the Siegel maps are giving us a way to compose things. All right, now who are the equivalences? These are going to be a higher dimensional version of being fully faithful and essentially surjective, which is what an equivalence of categories is. So like we said, for n equals 0, Thomson-Manian categories are sets, so equivalences are just bijections. For n equals 1, Thomson-Manian categories are just categories, so we have equivalences of categories. And then for n greater than 1, what we do is we say an n equivalence is going to be a map between Thomson-Manian categories such that it satisfies these two properties. So for the first one, we have a way of taking these are like Hom n-1 categories. So we have a way of taking these Hom n-1 categories, and we require that the induced map is an n-1 equivalence. So this is like the fully faithful condition. If we think of n being 1, then this would be saying on the Hom sets, we need to have a bijection. So this is the fully faithful part. And then our second condition is going to involve a functor that this functor P that I'm not going to define, but the idea is that we have a truncation functor that what it does is it divides out by the highest invertible cells. So again, if we're thinking about n equals 1, if we're thinking about categories, then where are the highest cells? These are just 1 morphisms because we just have cells up to n equals 1. The invertible ones are the isomorphisms. So when we divide by all these, we're taking iso classes of objects. So requiring that we have a bijection on iso classes of objects is another more complicated way of saying we are essentially surjective. So this is really the higher dimensional analog of our usual notion of categorical equivalence. And then finally, once we have these Thomson-Manian categories, we can define Thomson-Manian groupoids, which is what we actually care about for the homotopy hypotheses. So again, these are by induction. We're going to say the Thomson-Manian 0 groupoids are going to be the full category of sets. The Thomson-Manian 1 groupoids living inside of categories are going to be the usual groupoids, so the categories with all invertible morphisms. And then for n greater than 1, we pretty much just ask that whenever we fix a dimension, all of the lower dimensional multisimplicial objects are still of the Thomson-Manian groupoid kind. So of course, the reason that I am mentioning this model is because it satisfies the homotopy hypotheses. So if we take the geometric realization of a Thomson-Manian groupoid, remember this is nothing more than a simplicial set, a multisimplicial set, satisfying a bunch of conditions, but in particular, it's a multisimplicial set. So we can take its realization, and it turns out that is going to give us an n type. And furthermore, this induces an equivalence on homotopy categories. So this is an allowed model for n groupoids. All right, so now we're going to go into the second part of the talk where we look at the stable version of all this. So I guess this is a good time to pause for questions.
Maybe I'll just ask, can that last equivalence of homotopy categories does that come from a Quillen equivalence or something like that? Can you can you view it as arising from some sort of equivalence of model categories?
You know, I'm not 100% sure, but I think not.
Okay.
I think not, but don't quote me on that.
Okay. Thank you.
All right, so now we're going to go into the newer part of this talk, and this is where we make everything stable. So what does that even mean? Well, what I mean by making everything stable is that instead of studying topological spaces, we are going to study spectra. So what are these things? A spectrum is simply a sequence of pointed spaces together with structure maps. So these things that we call structure maps, and these have to be continuous maps from the suspension of xi to xi plus 1 for every I. And that is it. That is all that a spectrum is for the purposes of this talk. There's different variants, but this is really the most simple one, and this one's going to be enough for us. So if you've never worked with spectra before, you might wonder, like, this seems like a pretty unremarkable definition, right? It's literally just a sequence of spaces that are linked together with the suspension of one another. What is the point of these things? Well, actually, they turn out to be key objects of study in algebraic topology. So if you want a few reasons about why you should care about spectra, because I think we all agree that spaces are important, but there might not be such a consensus about spectra, perhaps. So here's a few reasons why spectra are important things to consider. They allow us to make sense of negative homotopy groups, which of course don't make any sense when we talk about spaces. They provide a natural setting for the study of stable homotopy groups. So you might have heard the buzzword stable homotopy groups of spheres thrown around in some topology talks. Well, this is like the natural setting to study these. They contain all the infinite loop spaces. So any infinite loop space can be given the structure of a spectrum. And so the spectrum in particular characterize all possible cohomology theories. And finally, we can look at spectra as an abelianization of spaces using May's recognition theorem. So really, there's a lot of reasons why topologists care about these, and this is actually not an exhaustive list. Like if you care about algebraic K-theory, for example, spectra are going to be there all the time, and I'm sure in a lot of other disciplines as well. All right, so now let's try to formulate the stable homotopy hypotheses. So what should be the analogous notion of n-types now in the world of spectra? Well, these are going to be literally the same thing. These are going to be spectra such that their homotopy groups vanish outside of 0, n. And now this 0 is not trivial, because remember, we can have negative things as well. But for n-types, the homotopy groups are only between 0 and n. So I should at this point maybe quickly mention what are the homotopy groups of a spectra? How are these things defined? Well, the ith homotopy group is going to be a colimit. And the colimit is taking over the diagram that we see down here. So we start with the ith plus jth homotopy group of xj. So these are just the homotopy classes of maps from the ith plus jth sphere into xj. And then we suspend everything here. So we get homotopy classes of maps between the suspension of the ith plus j sphere, but this is the ith plus j plus 1 sphere, into the suspension of xj. And now we apply our structure maps, which remember are part of the structure of any spectrum. And we apply them on this part right here. So this is going to induce a map from this suspension, which we said is exactly the ith plus j plus 1 sphere, into xj plus 1. And then we go on. So we have this infinite diagram, and the colimit of it is what we take as the ith homotopy group of the spectrum. All right, so now that we have homotopy groups, we can define weak equivalences as being the maps of spectra that give us isomorphisms on all homotopy groups. And as you might be wondering, these are in fact the weak equivalences of some model structure on the category of spectra. This is a result by Balsou-Friedlander. Right, so this settles the topological side, right? Because remember, the classical version of the homotopy hypothesis said that n types with weak equivalences are the same as n groupoids with higher categorical equivalences. Now, our stable version on the topological side will have stable n types with these stable weak equivalences that we just defined, and these are going to be the same as what exactly? So let's try to figure out what should be on the categorical side in the stable version. And the way that I'm going to do that is I'm going to draw intuition from infinite loop spaces. So like we said, any infinite loop space can be given the structure of a spectrum. And if you might be wondering, why is this an acceptable thing to do, to just look at these spectra and get all the intuition just from these and ignore the rest? Well, you might be comforted to know that the loop spaces are the fibrin objects in the model category of spectra. So it does make sense to just take them as the good objects that we're going to draw our intuition from. All right, so we're going to look at these infinite loop spaces. And the first thing that one notes is that we have a multiplication given by concatenating loops. And this multiplication is going to turn out to be associative, unital, and commutative up to higher homotopies. So what does this translate to on category land? Well, it translates to requiring our n groupoids to have a symmetric monoidal structure. So the multiplication of the loops is going to be seen in this monoidal structure, and the fact that it's commutative is going to give us this symmetric adjective. But there's something else that can be said about loops, and that is that it's that loops have inverses up to homotopy. Like we said, if we have a loop, then we can run it backwards, and then up to homotopy, that's the same as staying put. So since the loops are our objects now in the n groupoid point of view, we're going to say that the objects in the n groupoids also have to be invertible in some sense. So we're used to talking about maps being invertible. So what do I mean about objects being invertible? I just mean for every object, there has to exist another object such that when we take their tensor using this monoidal structure that we now have, we recover the monoidal unit. So it's really like when we deal with groups. In that sense, we're requiring inverses. So putting all this together, we're going to say that the categorical side in the stable homotopy hypothesis is going to be given by group-like. So group-like is exactly this condition of objects being invertible. So by group-like symmetric monoidal n groupoids, and we're going to call these Picard n categories. So now our statement is that stable n types are the same as Picard n categories. So just like with the classical homotopy hypotheses, there's a lot of work that goes into finding a good model of what Picard n categories should even be. So even before proving the hypotheses, we need to make precise what we mean on the categorical side. But before we do that, let me give you some evidence that this stable homotopy hypothesis makes sense, just by looking at the lower cases. So if we look at n equals 0, on the topological side, we have stable 0 types. These are what we call Eilenberg-MacLane spectra. And on the categorical side, we have 0 groupoids. So again, we only have objects and no higher cells. So in the classical version, we said these are sets. However, now we have additional structure because we also have a symmetric monoidal product on these things, making all the objects invertible. So in other words, so we have a set and we are allowed to multiply elements in the set. It has to be a commutative multiplication and everything has to have an inverse. So in other words, we have an abelian group. And the correspondence between Eilenberg-MacLane spectra and abelian groups is again something that is pretty familiar, let's say, to algebraic topologists. So the case n equals 0, again, is recovering something that we know. And now allow me to make make a small change in perspective. This might seem a bit artificial right now, but it's actually going to be crucial. We can look at these abelian groups in a different way. So we can shift one dimension up and describe an abelian group as a one groupoid with one object plus some added symmetry. So what do I mean by this? Let's say we have an abelian group. So what do we have? We have elements G1, G2, blah, blah, blah. We have a product. So we have a way of multiplying G1 times G2. And the abelian part tells us that G1 times G2 equals G2 times G1. So this is at dimension 0. What I want to do is I want to shift dimension and I want to look at this as something in dimension 1. So I'm going to categorify our notion of abelian group. So this is going to be a category, which I'm going to call G. So this category will have just one object. So that's why I'm saying a group with one object. And then the morphisms in this category are going to come to encode the objects of the abelian group. So since we only have one group, morphisms look like loops, if we look at this like a graph. And I'm going to say we have one such loop for each element in our abelian group. So how does this define a category? Well, we say the identity morphism is given by the identity element in the group, and composition is given by doing the product. So if you want to compose two loops, you multiply the elements of the group that they have in their labels, and you take the loop that has the product label, and that is the composite. So you can see that's why we're doing a kind of shift, because before the elements of the group were encoded as objects, and now we're shifting down and encoding these as morphisms. Okay, so this is going to encode, so this is actually not going to be a category, it's going to be a groupoid, because each of these loops has an inverse given by the one with the inverse label in the group. But what we're not encoding is this condition here. So we are not going to get that for free from the categorification, and we need to require that separately. That's why we have this plus symmetry condition up here. So in addition, we need the symmetry, which tells us that the composite of two maps is actually commutative. So this is going to be our way of looking at these abelian groups as a one groupoid with one object plus some added symmetry. All right, so after that digression, let's go back to the hypotheses. And unlike the classical case where n equals 1 was a familiar statement, here n equals 1 is already non-trivial. So this is the statement that stable 1 types correspond to Picard categories. This was proven formally, I think, at first by Patel. And then if you allow me to do this shift in dimension again for this case, instead of looking at these Picard categories as groupoids with a symmetric monoidal structure and invertible objects, I'm going to shift down and look at them. So here we were at n equals 1. I'm going to go to n equals 2 and look at these as groupoidal bicategories with one object plus some added symmetries. So really the same shift that we just did. And then n equals 2 is the statement that stable 2 types correspond to Picard bicategories. This is already very, very technical. This was proven by Gursky, Johnson, and Osorno, I think 3 years ago. And this is it. So this was the state of the art in terms of the stable homotopy hypotheses. N equals 0, 1, and 2. So what we set out to do is to generalize this. So we set out to give a notion of Picard weekend category that satisfies the homotopy hypotheses for every n. So you might be wondering why can't we just copy the definition that we have so far and replace the specific number by an n, and then just go ahead and take that as the definition of Picard weekend category? Like, why do we even need to construct a new model for these? So remember, we just had the Picard 0 categories are group-like, groupoidal, symmetric, monoidal 0 categories, which is probably the ugliest way you've seen to describe an abelian group, but this is really all that they are. And then Picard 1 categories are group-like, groupoidal, symmetric, monoidal categories. Picard 2 categories are group-like, groupoidal, symmetric, monoidal bicategories. So why don't I just say Picard n categories are group-like, groupoidal, symmetric, monoidal n categories? Well, if you've ever worked with higher categories, you will know that symmetric monoidal bicategories are already really hard. There's a lot of bookkeeping involved when working with these. And there's not even a definition of symmetric monoidal n category for n greater than 4. So these are structures that are so hard to deal with, you don't even find them in the literature. They're kind of untractable. So we can't just try to get away with putting an n in this general statement, because that's not even a notion that we can deal with. The problem is that the symmetric monoidal structure on the n categories becomes way too hard. So the key is going to be to use the perspective that I was outlining before about doing this dimension shift and letting the dimension shift encode the symmetric monoidal structure for you. So when we said before, a Picard n category is a group-like symmetric monoidal n groupoid. Now we are going to encode the monoidal part by shifting one dimension up. So a monoidal n groupoid is the same as an n plus 1 groupoid with one object. So we have the monoidal part down. Now for the group-like part, note that the original objects, just like we did with the abelian group example, what were then objects are now morphisms. So what were then 0 cells are now going to be 1 cells. So requiring that these are invertible is already coming for free, because now they are 1 cells in a groupoid. So these have to be invertible because we are in a groupoid. So this part is coming for free from encoding this in a higher groupoid. And now what we're missing is this symmetric adjective. Just like we had with the abelian group, this has to be encoded separately. So how can we encode the symmetry? Well, first of all, I'm going to highlight every time that I'm saying n groupoid here, because like we said at some point, this is a very vague notion, and in order to make it precise, you need to pick a model. So I'm going to go ahead and pick the Thompson-Money model. So how do we encode the fact that the monoidal product is symmetric? Well, remember, a Thompson-Money n+1 groupoid with one object is a functor from n+1 copies of delta op into set, satisfying a whole lot of properties. And what we want is the composition to be commutative. But how do we compose? Well, the whole point of using these multisimplicial models is that we compose using the Siegel condition. Remember, we can invert this up to homotopy and get a composite. So how can we turn this into a symmetric composition? Well, in order to introduce this symmetry, the trick is going to be to pick out one of the deltas from the n+1 many copies. We're going to pick out the first delta and look at this as a functor from delta op times delta op and n to set. And we're going to change that delta op to a gamma. So if you remember, delta op is the category of finite sets and order preserving maps. So it's the op that is delta. And now gamma is going to be the category of finite sets, finite pointed sets, and base points preserving maps. So we go from having only order preserving functions to having base point preserving functions. So we only have a condition on the base point, but away from that, we can do whatever. And this is actually going to be the key. So how do we use that to encode a symmetry? Well, if we now look at our functor and extend it to a functor from gamma times delta op n to set, by using this embedding that we have from delta op into gamma, then our composition is not going to use the D1 map in delta op anymore. Now it's going to use the image of that map through the embedding. So it's going to be this phi D1. And this, if you just trace what the embedding does, this is just going to be given by the map from 2 to 1 that takes both 1 and 2 to 1. So we're taking 0 as the base points here, take 0 to 0, and 1 and 2 to 1. So why is this so crucial? Well, the key thing is that in gamma, now we are allowed to twist. So we can now go from 2 to 2 and twists the elements 1 and 2. We couldn't do that before in delta op because that wouldn't be order preserving. But now that we have this twist, we can observe that this phi D1, the map taking 1 and 2 to 1, is the same as first twisting 1 and 2 and then doing phi D1, just because everything goes to 1, so it doesn't really matter if you twist them or not. But it doesn't really matter at the level of gamma. But what this is telling us is that these two things have to induce the same map at the level of the simplicial things. So it's going to induce the same map from x2 to x1, whether we pick the composites like that or like that. So this is exactly encoding the fact that the composition has to be commutative. All right, so now that we are encoding all of the features that we said we need, we have a proposed model for Picard-n categories, and that is that a Picard-n category is going to be a functor from gamma times delta op n to set, such that when we restrict the first coordinate also to gamma op, we obtain a Thompson-Money n+1 groupoid with one object. And the equivalences are just going to be the equivalences of Thompson-Mani n+1 groupoids once we do this restriction. All right, so now let me tell you how do we connect these homotopy categories? So the homotopy category of these things that I just defined and that of stable N types. And the key concept to do this connection is going to be that of gamma objects. So whenever we have a pointed category C, we can define a gamma object in C simply as a functor from gamma to C mapping 0 to the point. And if furthermore our category C has weak equivalences, we can add an adjective to these gamma objects. And we say a gamma object A is special if for each K, the map from AK to K many copies of A1 is a weak equivalence. So you might be getting a flashback from our Siegel condition. If so, that is perfectly true. These are related. So in particular, the categories that we are going to be interested in are pointed simplicial sets. So I'm going to take the freedom of modeling topological spaces by using pointed simplicial sets, and also Thompson-Mani n groupoids. So both of these are pointed categories with some notion of weak equivalence. So we are allowed to take special objects. And note that this new Siegel condition, quote unquote, on special objects is going to make the set pi0 of A1 into an abelian monoid, because now we're saying this has an inverse. So just like we do with the Siegel map, where we flip the first one, we get a product in pi0 of A1. So this is the fact for all special gamma objects. And we're going to say that a special object is very special if this abelian monoid pi0 of A1 is a group. So this may or may not happen, but when we have inverses, we call it very special. So now I'm going to put all this together and show you a sketch of the proof that Picard N categories are the same as stable N types. So this starts by looking at the model structure on pointed simplicial sets. So we have a model structure here, and we can leverage that model structure to define a model structure on the gamma objects on pointed simplicial sets, simply by saying weak equivalences are defined level-wise. So we have a model structure on gamma simplicial set. And if we restrict to the very special object, that gives us a homotopy equivalence to the spectra with homotopy groups on the positive part. This is a result by Bousudel-Friedlander. So this is known. Spectra with only positive homotopy groups can be modeled through very special gamma objects in pointed simplicial sets. So what we do is we specialize this to N types. So if you restrict to N stable types on the right, and you restrict to N types on the left, then we prove that these functors still have the correct domain and codomain, and that this still gives an equivalence at the level of homotopy categories. And then on the other hand side, we have the classical homotopy hypothesis, which was the statement that Thompson-Mani n groupoids are the same as spaces whose homotopy groups are in 0n. So again, this is the statement due to Thompson-Mani, and this is already specialized at level n. But what we are going to do is we're going to take very special gamma objects on both sides. So we show that if we take very special gamma objects on both sides, you still get the homotopy equivalence. You still get an equivalence between their homotopy categories. And now we are almost done. So if you look at this composite, On this side, we have stable n types. That is exactly what we want. And then on the other side, we have these very special gamma objects in Thompson-Mani and groupoids. And the claim is that we are done because one of our main theorems gives another characterization of Picard n categories. So we prove that a functor from gamma times n copies of delta up to Z is a Picard-Thompson-Mani n category. Remember, this was just a functor such that in the underlying gamma first coordinate, we get a Thompson-Mani n+1 groupoid with one object. We prove that that characterization is equivalent to requiring that this functor be a very special gamma object in Thompson-Mani n groupoids. So if you do a clarification and you put this gamma, this delta op over there, this can be seen as something from gamma to delta op n set. And we require that this have the very special condition. So these two things being the same means we can put our Picard-Thompson-Mani n categories equivalently here. And now this composite gives us the stable homotopy hypotheses. All right, that's all that I wanted to tell you. Thank you so much for listening. John, I think
thanks very much. And we usually have a silent round of applause for our speaker. So thank you. And yeah, that was very interesting. And if anyone has a question, feel free to unmute yourself and ask.
I have a question, maybe.
Go ahead.
So, is it possible to express the definition of Picard n category as a multisimplicial set with some condition on a, I guess, left-kind extension? Expanding the domain of the functor from delta op n times to gamma times delta op n minus 1 times.
Oh, I see what you mean. Perhaps. I mean, we're just taking it as we're just directly taking it as a functor from gamma. So we're like letting go of the previous guess that it would be a functor from delta op, and just taking as the definition a functor from gamma. Can that be seen as a Kohn extension? I don't know. Maybe.
Okay.
Any more questions? Well, if not, then let's thank Maru again for a really nice talk. Thank you. Okay, well, that's it for today. So thanks very much for coming, Maru. And yeah, I'll